Let's look at another problem that has to do with Bayes' theorem. So this problem I'm calling problem 2. It says an automobile insurance company has determined the accident rate, probability of having at least one accident during a year, for various age groups. Suppose that a policyholder calls in to report an accident. What is the probability that they are over 60? And then we have a table of data. Let's take a look at this table of data. The left-hand column is called age group. So we have drivers under the age of 21, drivers between 21 to 30, 31 to 40, 41 to 50, 51 to 60, and over 60. In the middle column, we have the proportion of total insured. That means out of all of the people insured with this particular company, the 100% is divided up between these different age groups. This 0.05 tells us that 5% of the policyholders are under the age 21. 10% are between the ages 21 to 30. 25% are between 31 to 40. And we can continue to see the trend. If we add all these numbers up, we get 1, which represents the 100% of policyholders. The next column is the accident rate. The third column is accident rate. It is the rate at which each of these age groups would call in for an accident. Let's take a look at the actual problem. The problem had said, suppose that a policyholder calls in to report an accident. So that's the given. And we want to know, what is the probability that they are over 60? Down below, in probability, this would be written as the probability of over 60, given it was an accident called in. Now, in actuality, the calculation is to find the probability of someone being over 60 and having an accident, divided by all of those having had an accident. So we have several calculations to take care of to find these different pieces. First, I need to know the probability of having an accident. The probability of having an accident requires all of these intersections to be calculated. The probability of being under 21 and having an accident. Then the probability of being 21 to 30 and having an accident, and so on. Now, I find the easiest way to find these intersections is to go up to the table and create myself a row to the right. So the intersection of being under 21 and having an accident is 0.05 multiplied with 0.06. And this ends up being 0.003. Similarly, I multiply the 0.10 with the 0.04, and I got 0.004. In the next row, I got 0.005, 0.003, 0.0075, and 0.004. Now, when I added these values together, I found that I had a value of 0.0265. Now, this is actually the probability of an accident overall, regardless of age. And so our probability of having an accident, I'll just call it A, is 0.0265. But to solve the actual problem, I needed to know the probability of being over 60, given an accident was called in. And that we had noticed is the intersection of 60 and accident divided by accident. So the probability of being over 60 and having an accident is 0.004. We're dividing that by the total probability of accidents. This ends up being 0.1509 and several other decimal places. If I were to round this to 3 decimal places, it would be 0.151. What that means is that there is a 15.1% probability that an accident that is called in is by a person that is over the age of 60.